Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we discussed the first law of thermodynamics. We used this law to help solve problems and found a few different ways in which this law can be expressed. Today, we will be relating this law to the isobaric, isothermal, and isochoric processes we introduced earlier. We have much to talk about, so let us begin. Do you remember the isobaric process, everyone? This is the process in which the pressure of a gas remains constant. Any work done by the system will increase the volume. Consider this pressure-volume diagram. Notice how when work is done, the volume increases, but the pressure does not. We can infer a basic equation for isobaric processes based on this relationship. Work done is equal to pressure times change in volume. How does this relate to the first law of thermodynamics? Let us try substituting what we have observed into the equation. Instead of an increase in energy being equal to energy transferred plus the work done on the system, the change in the internal energy is equal to energy transferred plus pressure times the change in volume. At this point, it is important to note that since in the original equation, delta W represents work done on the system, this value must be modified. In isobaric processes, work is done by the system. Therefore, we replace the positive value for a negative value. Therefore, using the first law of thermodynamics to resolve a problem in an isobaric process, we use the equation delta U is equal to delta Q minus P delta V. In isochoric processes, the volume of the system remains constant. Thus, there is no work being done on the system. Since we established that the increase in work is equal to pressure times an increase in volume, we can safely say change in volume and work done must equal 0. Thus, in an isochoric process, the equation is written as increase in internal energy is equal to energy transferred. Isothermal processes occur at constant temperature. So there is no change in the internal energy of a system. So we know the value of delta U is 0. Again, we can substitute this information into the first law and arrive at the following equation. the amount of energy transferred is equal to work done by the gas. Let us make sure we can identify these correctly. Here are 4 pressure over volume diagrams. Can you identify the process occurring in each? Which equations are applicable to each? You may begin, students.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Hello, everyone. Did you manage to label every diagram correctly? The first diagram demonstrates an adiabatic process. This is identifiable from the fact that volume increases and pressure decreases as work is applied. Thus, the equation is delta U equals negative W. The second diagram is an isothermal increase in pressure. The equation for an isothermal process is delta Q is equal to W. The third diagram is an isobaric process, as it has constant pressure. The correct equation is delta Q is equal to delta U plus P delta V. The last one was actually unidentifiable at this stage and is called isochoric process. We will focus on adiabatic processes in more detail in our next lesson. To calculate changes in gas temperatures, we can use the molar heat capacity, which is the heat capacity per mole of substance. However, depending on the conditions under which heating occurs, we may be seeking one of two different quantities to resolve a problem. The first is the molar heat capacity at constant pressure, which is represented by C sub P. The second is the molar capacity at constant volume, represented by C sub V. Both possess the unit measurement of joules per mole Kelvin. If N is the number of moles of gas being heated, and the heat applied results in a rise in temperature, then we can write the equation as follows. Molar heat capacity at constant pressure is equal to heat transferred at constant pressure over the number of moles times the change in temperature. We can also infer the same equation for volume. Taking into consideration, we must replace the P subscripts with V. Once again, this satisfies the first law of thermodynamics. So, at constant pressure, heat transfer is equal to the increase in internal energy plus the pressure times the change in volume. If the quantity we are seeking is constant volume, then heat transfer is equal to the increase in internal energy. In order to produce an equal increase in internal energy and a subsequent increase in temperature, a greater amount of energy must be transferred by heating a gas at constant pressure, then by heating a gas at constant volume. Molar heat capacity at constant pressure is always greater than the molar heat capacity at constant volume. A few lessons ago, we also introduced the molar gas constant, which is applicable in this equation, called Meyer's equation. It states the difference between the specific heat of a gas at constant pressure and its specific heat at constant volume is equal to the molar gas constant. The ratio of constant pressure to constant volume is commonly written as the Greek symbol gamma. Given the values for specific molar heat capacity for an ideal or monatomic gas, we may write this equation. Gamma equals Cp over Cv, which equals 5/3. However, for diatomic gases, the ratio is 7/5. Here is one more activity, students. Here are two gases. What are their molar ratios?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. This activity was easy, but it also illustrates a valuable point. The molar ratio of nitrogen gas is 1.4, while the molar ratio of hydrogen is 1.4. Therefore, these two gases are very close to an ideal gas form. This concludes today's lesson. Today, we have learned about the relationship between the first law of thermodynamics and gaseous processes. Until next time, thank you, teacher. Thank you, students.